Welcome to another lesson. It has been mentioned before that only two pieces of information are needed to define a line, right? 2 points or 1 point and a slope. Well, we've been talking about quadratic equations, okay? That is second order polynomials. And it may seem reasonable that 3 pieces of information are required to determine that. Whether it's the 3 coefficients, right? Ax squared plus bx plus c, so 1, 2, 3, or remember from vertex form, okay, we have 1, 2, 3 pieces of information, okay, or graphically, it could require three coordinate pairs, okay, 3 coordinate pairs. In fact, higher order polynomials, so if we went to y equals ax cubed plus bx squared plus cx plus d. 1, 2, 3, 4 pieces of information. And likewise with the 4th order, 5th order, etc. We're not going to focus on those today. I'm just throwing that out there for your curiosity. But let's explore, why is this the case? Why do we need 3 coordinate pairs to define a unique quadratic equation? Well, let me draw my Cartesian plane. Let's do a simple example. Let's say x minus 1, x minus 5. Y is equal to that. All right, so remember the roots, the zeros, the x-intercepts, okay, there's a lot of different things we can call it, correspond to these factors. So a 1 and a 5, I can put a dot here, 1, 2, 3, 4, and a dot there. Okay, now if I FOIL it out, first, outer, inner, last, I'm going to get x squared minus 6x plus 5. Okay, then I could use the table method to plot the points. X, Y. Well, all right, 0, 1, 2, 3, 4, 5, and 6.
0 squared minus 0 plus 5 is 5. Easy enough. 1 squared minus 6. So 1 plus 5 is 6. That's 0.
Okay, no surprise, right? We saw that coming.
2 squared is 4. Plus 5 is 9. Minus 12 is a negative 3. Okay. 3 squared is 9. Plus 5 is 14. Minus 18 is a minus 4.
By symmetry, I should expect the same thing on the bottom.
So 4 squared is 16. Plus 5 is 21. Minus 24 is negative 3.
So behold, it matches.
5 squared is 25, plus 5, 30, minus 30 is 0.
Okay, again, no surprise. So we have negative 3, 0. What do you think the 6 is going to spit out?
36, 41 minus 36 is 5. Okay.
So I put my points here. 1, 2, 3, 4, 5. All right, negative 3. 1, 2, 3. Negative 4. Negative 3, and a 5. All right, I draw this. That's my parabola. That's my graph. Now, all right, to make it easy, let's pick these 2 points. They lie on the x-axis. You say, because okay, let's rewind. What's the whole point of this discussion? It's to show that 3 coordinate pairs are necessary to uniquely define a quadratic equation. Uniquely means this is the only parabola that passes through these 3 points, or these 3 points. To make it simple, I am going to multiply by 2. X minus 1, x minus 5. All right, well, this is going to be the same, so I'm just multiplying each of these terms by 2. So y equals 2x squared. 6 times 2 is 12. 5 times 2 is 10. Okay? So, table method, x and y. 0, 1, 2, 3, 4, 5, 6.
Plug in a 0, I get a 10. Plug in a 1, I get 2, 1, that's 0. Okay, plug in a 2, I get 4 times 2 is 8, 18, minus 24 is a negative 6. 3 squared is 9 times 2 is 18, plus 10, 28, minus 36 is minus 8. Okay, and symmetry. 4 squared, 16 times 2, 32, plus 10 is 42, minus 48 is negative 6. 5, 25 times 2 is 50, plus 10 is 60, minus 60 is 0. And 6. 6 squared is 36 times 2, 72, plus 10, 82, minus 72 brings us back to 10.
So notice the symmetry. Negative 8, 3, negative 8. That's going to be our vertex. Remember the lowest point. Negative 6, 0, 10. Okay, it has that symmetry about a vertical axis. If I were to plot this, well, I'm going to be off the charts somewhere up here and over here. 0, boom, boom. That's already there. Negative 6 is going to 1, 2, 3, 4, 5, 6. That's going to be down here. And 8 is another. So, okay. So we see there are 2 different parabolas that pass through the same 2 points. And in fact, I could multiply this by a 3 or a 4 or a 1/2 or a 1/3 or a 0.628, whatever number I want, I can multiply. So we have an infinite number of parabolas that pass through the same 2 points. Right? In this case, this is an example of dilation, like stretching it or compressing it, but they all pass through the same 2 points. That is why we need a third point to say which one am I talking about. Is it this one with a vertex here, or this one with a vertex here? Okay. By the way, you don't need to restrict yourself to the x-intercepts and the vertex. Those are just the simplest to demonstrate this concept on. I just wanted you to see why 3 coordinate pairs, 3 points are needed to define a unique parabola, just as 2 points are needed for a line. So hopefully that made sense. Feel free to discuss it below in the comments. If you enjoyed this video, like it, subscribe to my channel so you can keep getting more videos like this. And I'll see you next time. Thank you for watching.